Okay, so last time we had shown these two properties, that for the measure gamma, uh, measure of determinant is exactly d choose k square, and measure of determinant is, if you assume that determinant has a depth 3 circuit, then it will be at most SQ alpha d. Okay, so all we have to do is now pick a k and alpha so that you get a exponential lower bound on S. Right, so we want to isolate S here. So for that we simply have to do some calculation using Stirling's approximation. So log of n choose epsilon n is essentially a multiple of n, where the multiplier is entropy function. And so for example, n choose epsilon n from this, so h2 epsilon is around minus epsilon log epsilon, right? So that gives you 2 raised to omega n, where constants will depend on epsilon. Okay, so if epsilon is for example half, right, then this is coming out to be around 2 raised to n by 2, 2 raised to in fact n, 2 raised to n, and then in the exponent the minus error term is very small. It's something like 2 raised to n the whole thing divided by square root n. Okay, so the error term is only half log n, which is also what we have mentioned here. Yeah, but this is not true for all epsilon. So obviously if you go far away from half towards 0 or towards 1, then you will be in a problem. Then choose epsilon n will not be so large. So that is why we have to do this calculation to fix things. Okay, so let us take log both sides. So that will give you, on the LHS you will get log of d choose k square, which is so using that formula you get d times h2 and d over k, or k over d, sorry. Yeah, you are saying
LHS is log of this, right?
d choose k, d choose k. This is the equation, inequality. So omega d times entropy, which is omega d times k over d is, yeah, so that we have to read it from here. Q over d is depends on tau over d, which is alpha, so alpha over 10q. So which suggests that alpha will depend on q, okay, which is why we assume q to be constant. And so we get that log s is, again from that equation, from here we get that log s is omega of minus alpha d log q. So we can take d common. So you get what do you get? You get H2. So the entropy is then, use the definition, right? So entropy will come out to be alpha over 10q that is entropy minus d alpha log q. Right, so many things here are actually unimportant. What is important is just if we can make sure that this part, so think of this as the main part. If this main part is large enough, right, then the main part will be able to compensate for this error term, which is minus alpha log q. So we just have to compare these two, because the remaining part is it is already a positive contribution, so we don't care about the positive contribution. We just care about this main positive cancelling with the negative, right? So that's all. So we'll just pick, it suffices to pick alpha c such that log of 10q over alpha is greater than some constant times alpha log q. Okay, so then the main part will be a multiple of some constant times alpha log q, which will give you no, sorry, not alpha, making a mistake, cq log q. This. So this is, if this is more than q log q, then you get yeah. So you get alpha over 10q multiplied by this will give you c alpha log q, which you pick bigger than the negative error term. Is that clear? So you just pick constants alpha, well, constant c at least, and alpha is something that is really dependent on q once we have fixed the constant c. So this is actually an absolute constant, and this is a function of q. So you will see how the dependence on q is, right? So this is inequality holds if and only if alpha is less than 10q divided by qcq. So it's equivalent inequality, and so that fixes your alpha as a function of q only. And once alpha is fixed, so that fixes your tau, and once tau is fixed, it fixes your k, right? So all the parameters are fixed. That fixes your tau. So what this means in the end is this part here, the RHS here, with these calculations, this essentially becomes a positive constant, right? So log s over d is more than a positive constant, which means that s is more than 2 raised to d, 2 raised to omega d. So for constant q, tau makes sense. what do I mean by make sense, right? So remember that our proof used tau to divide into cases, whether the rank is less than tau, more than tau. So we are using the fact there that tau is some integer bound, right? So in case q is very large, so since you are dividing d by q raised to q, so if q raised to q, for example, is d or more than d, then tau here is a fraction, right? So that will not give you anything. So you can, I think this proof will work as long as q raised to q is sufficiently smaller than d. So certainly if q is square root of log d, the proof is fine. Or when q is just below log d divided by log d, that is the limit of this proof. And this tau then appears also as constants in the omega. The lower bound constants are actually dependent on tau. Yeah, that actually is the formal reason. Log s is kind of dependent on tau. So if tau is very small, then you don't get any lower bound. Otherwise, you will just get that log s is omega dependent on q d. So that finishes the proof. You get s equal to 2 raised to d, 2 raised to omega d. Constants depend on q, and this works up to q smaller than log d over log d. Is this clear? So it is an open question to make it work for larger q's, larger finite fields. So if the field is really growing with the degree parameter, then what do you do? Then is it possible that determinant or permanent d cross d can be expressed as a sub-exponential depth 3 circuit? So that we don't know. Other remark is this minor optimization, that why are we getting 2 raised to d, why not d raised to d lower bound, which will be the optimal lower bound. So obviously we cannot get that for permanent because it is false. For determinant, we don't know, but we can change the polynomial. We can look at some other polynomial, and then it can be shown. So the lower bound can be improved by considering a sum of, well, not sum, just elementary symmetric polynomial. And it will be elementary. So if you look at elementary symmetric polynomials, then the lower bound can be optimized. So this is a polynomial on d square variables like determinant, and like determinant degree is less than equal to d, but its definition is very different. So it is actually it's a sum, yes, less than equal to d. So it is defined as so I should say sum then. So it's a sum because we are looking at all the monomials, not just for subsets of size d, but also d minus 1, d minus 2. So it's a sum of these first at most d degree, or the first d symmetric polynomials we are just summing up. So it is inhomogeneous. It's a bit different from determinant, and the definition will give you depth 3 circuit of size already n to the d, right. So n to the d is kind of d raised to d, d raised to omega d is by definition, and that can also be shown as a lower bound by the previous proof. So it's optimal. Of the matrix M K sim less than equal to D, F Q to the N, this rank is greater than equal to N choose D by 2. If you take K to be D by 2. So basically the rank lower bound argument in the previous proof can be improved. The rank upper bound argument on depth 3 circuits remains the same, and then you match the two and you will get this lower bound. You will get the lower bound of n to the d. So that's optimal.
And in this case, how large can Q be?
No, the proof is the same.
Rest everything remains the same. I mean,
Calculations are all the same. Just in the case of determinant, we could only show a rank lower bound of this d choose k whole square, which is anyways bounded by 2 raised to d, 2 raised to omega d. That was the fundamental limitation. Now we go slightly above 2 raised to d. So I guess one syntactical difference, it may be an important difference, is that there we were getting in the lower bound d choose k, where d was the degree, right. Here we are getting n choose d, where n is the number of variables, which is d square. So that d square actually gives you the kick, because this simple combinatorial estimate will be n divided by d raised to d. So that will become d square by d raised to d, that is d raised to d, right. So that is where the improvement is coming from. So compare it with d choose k. N is d square, so this is much better. Any questions? Okay, so then we will move on to the next model and the next lower bound. Okay, the technique will not change drastically. It will be a smooth generalization of what we just saw, which is look at the matrix of derivatives at a point, and in fact at several points. So the matrix of derivatives was the derivative was being evaluated at many points. So that definition will slightly change. We will continue to look at derivatives, but in a slightly different way. Matrix will be slightly different, and the depth of the circuit will now start looking at more depths, not just depth 3. So restriction will be multilinearity. So multilinear models. So what is that? Yeah, so your circuit ultimately will compute a multilinear polynomial, which means that individual degree of every variable is at most 1, but moreover every gate will do that. Yeah, but for today we will not look at the gate, so that second thing is not very important. So just think of multilinear polynomials for now, for today's lecture. So multilinearity is a natural restriction on circuits. So our most fundamental polynomials like determinant and then permanent, symmetric polynomials, etc., they're all multilinear. So you can ask the question that if the final polynomial is multilinear, um, would it help if we used non-multilinear monomials inside the circuit? Right? Maybe you can get a circuit that does not use x square, for example, at all. So can they be computed without computing monomials like squareful monomials like xi to the j for j greater than 1. Right? So can we do without this xi square, xi cube? Because ultimately you have a feeling that these things will anyways get cancelled, right? So how can their uh, incorporation in the circuit help in computing determinant? So is this intuition correct? What do you think about this simple-minded intuition? Can squareful monomials help you in computation?
You can just go modulo that ideal at every step, right?
Yeah, but then mod computation has to be done. That's even harder.
Mod computation at every step is the same as mod computation throughout. So if you add any squareful monomials in the middle, you can just kill them, right?
How? There are too many.
I said
How?
for an existence result, you don't need.
No. Ultimately, you have to then eliminate mod gate. So how do you eliminate mod gate by addition multiplication?
Probably recursively, or like if you want an existence result, then
Yeah. So you are making bold conjectures. Yeah. So for now, all we know is our first algorithm for determinant was using sum of powers and Newton identities, right? So although there was no reason, there was no monomial in the in determinant, which is squareful, where the individual degree is more than 1, but still we started actually with the sum of powers, right, inherently against multilinear computation, and that helped in the final circuit. That so every gate is actually working with these non-multilinear monomials. It is absolutely not clear how to remove them. So then you may think about the second algorithm, which is ABP, it's the Mahajan-Vinay thing, and there also you would see that this the closed walks, they keep repeating the variables with the non-multilinear monomials, and there is no clue how to eliminate that, right? So this intuition may be plainly wrong, but well, the question is well formulated, so we continue. So we try to understand why, for what models will non-multilinear monomials help us, and for what polynomials. Okay, so a circuit C is multilinear. If every gate computes a multilinear polynomial. Okay, so we'll gradually prove bigger and bigger results. So we'll start with the depth 3 model with this restriction, so multilinear depth 3, and then we'll look at more general models. From depth 3 we'll move to constant depth, from constant depth we'll move to formulas. So we'll first focus on multilinear depth 3 and exponential lower bounds. So the thing about multilinear model is, and why this has been studied so much, is this partial derivative idea works very well in under this restriction. So we'll continue with the measures that use partial derivatives. In fact, this partial derivative space. So the measure that succeeds here is a twist on what we did in the previous proof, in the sense that it will not just look at the space of all the derivatives. That may not be refined enough to give you a result. It will actually look at specific derivatives, and in particular we will partition the variables into two parts depending on what kind of a circuit we are looking at, and the derivatives will be then the matrix of derivatives will be rows indexed by monomials in one part of the variables and columns indexed by monomials in the other part of the variables. Okay, so that is a departure from the previous definition. So it's a more refined measure than just look at all the derivatives. So partition the variables x as y disjoint union z, so for a monomial my or respectively mz in the y variables respectively z, let coefficient of my dot mz in a polynomial f, f has variable set x. So what is this? This is just what it says. So note that my times mz remains a multilinear monomial because y and z are disjoint. So we are just asking for the coefficient of this monomial in f, right? It may still be 0, but it's not always 0. Somewhere maybe we write down that f is multilinear in over a field variables x. So multilinear polynomial. So coefficient, this coefficient in f this is also equal to, so the coefficients are actually in general also they are related somehow to the derivatives, right. So this is also you differentiate f. Is this enough? Yeah, so problem with this derivative is, yeah, so if you look at the polynomial y times z square, let's say y and z are just single variables. So if you look at yz square and you differentiate by y, differentiate by yz, then you will get 2z, right? But that is not a coefficient. In fact, in the polynomial yz square, the coefficient of yz is 0, right? So there is a slight gap between derivatives and coefficient, and that gap is filled by saying that derivative at the point 0. Okay, so you differentiate by this monomial and then set all the variables to 0. That is what gives you the corresponding coefficient, right? You can see this as a simple exercise. Particularly for the multilinear case. Otherwise, you have to generalize this slightly. Do you have to generalize it, or is it always? It's always true. Yeah. So there is a short proof for this. Right. So instead of saying this derivative at 0, we'll just say coefficient of f. It's the same thing. And then we have a matrix whose rank will be the measure. So define matrix M, Y, Z, F as so monomial My is here, Mz is here, and use this coefficient or extract coefficient My times Mz, coefficient of the monomial My times Mz in F. So these are all the monomials in Y. In fact, sorry, not Y, Z. Multilinear monomials, we only care about them. And these are all the multilinear monomials in Y. If the degree of f is d, then you just look at multilinear monomials in Y or Z of degree up to d. So that is it's a finite matrix. So entries are either 0 or non-zero constants from the field F. Many of the next lectures, these methods will be field independent. So I will not talk much about the field. Okay, now from now on, many of the methods are actually field independent methods.
I have a question. So in every entry which is corresponding to some y and some z,
right?
This y and z is a partition.
Yeah, y are the y variables, z are the z variables, x is the universal variable set.
Because there are many yz's, right? So in that.
No, y, big Y is the variable set. Let's say the left variables, and z, big Z is the set of another variable set disjoint from big Y. Let's call this the right variables. And you look at all the multilinear monomials in the left variables versus all in the Z variables, and then draw the matrix, where entry will be of the product, corresponding to the product. Extract the coefficient. So, like if you may have y1, y2, z1, or if you use x variables, we can write in terms of that x1, x2, and z is x3, x4, and then you have here 1, x1, x2, x1, x2, and there you have 1, x3, x4, x3, x4. So it's a 4 by 4 matrix, and yeah, you don't have any other monomial possible. So you have 16. So in general, you will have here that many.
2 raised to y call rows and
Yeah, so it is not really dependent on the degree. So it just use everything. So 2 raised to size of y many, and 2 raised to size of z. So overall, you have 2 raised to y plus z many.
because there was, so I was confused because there was m y, so that y was representing general partitions.
So 2 raised to x is equal to 2 raised to y plus z. That's so it's basically that. So we are looking at all the multilinear monomials in the end, but how we will draw the matrix, that will obviously change the rank and the measure. So what is y and z? That will change everything actually. It will be hard work, and later on very hard work, to identify the y and z. It will use a lot of probability theorems. It will be done probabilistically.
So choosing partition is tricky.
Yes. No, sometimes this method will just probably fail. There will be no partition. It's not a general method, which is why we have put all the restrictions, and we'll put more or other restrictions. Yeah, it will work for constant depth multilinear circuits and multilinear formulas. Yeah, so it's that's a surprise. These are major results. Okay. So once we have that definition, we also get the measure. Gamma y z f. This is the rank of the matrix over the field. And this matrix is also called partial derivative matrix of f. Which is an incomplete name because it's not just all the partial derivatives, but how they are arranged. So it partial derivative matrix of f with respect to a given partition, and its rank is what the measure is. So as experienced before, this measure will have nice properties. So when you have f1 plus f2 and f1 times f2, the measure will behave well. It behaves well under ring operations. So unsurprisingly, it has sub-additivity. Which is gamma of, so I suppress y and z now, let them be fixed. So gamma of f1 plus f2 is less than equal to so gamma of sum is at most sum of the gammas. How do you show this? Right. So the coefficient operator is linear, and this is obviously inherited from the derivative operator being linear. So you have two matrices, one each for F1, F2, and then use, so follows the rank property. Of A plus B for matrices AB. So rank of A plus B is at most rank of A plus rank of B, just that. Right, and you know that this is the best you can say. It can be strictly smaller. So it's not additivity but sub-additivity. And second is multiplicativity. Yeah, so here we want to, this will be tricky. So here we want to look at gamma of F1 times F2, but we'll have some assumptions, right, which is that F1, F2 have disjoint variables. So since F1, F2 have disjoint variables, you can think of each of these variable sets having their own partitions. So there are actually 4 variable sets. So in those terms we will write. So gamma y z f1 f2, and there will be an equality. Where y is y1 disjoint so y1 y2 z1 z2 partition y and z respectively, and f1 is in y1 z1. F2 is in the rest. Okay, those are the assumptions. So F1 is basically on the variables y1 union z1. So it has its own measure, its own matrix, and F2 is on y2 union z2 variables. It has its own matrix, and then when you multiply them, then you will take essentially the row variables of F1, row variables of F2 union, and the same thing with columns. Is the statement clear? So what is the proof of this? Right, this is strong. This is a perfect equality. So already multilinearity definition of a circuit is being is motivated by this. This is the property that will demand that every addition gate, the addition gate isn't important. The multiplication gates, they should all be computing multilinear. Hence, the input to a multiplication gate should be disjoint variable.
Because of multilinearity, y and y2 are disjoint.
Right. Yeah, so let us define the matrices and then, well, so M, Y, Z, F1, F2, first matrix, second matrix is, and third matrix is, so who will guess the relationship between these three? Oh, we have read the survey. Yeah, so if you look at the rows in My1 and My2, the rows are in completely different variables, right? And the rows in Y they are all the monomials in Y union Y2. So there is this construction in matrix called tensor product. So that will perfectly match this index set. So if you take the matrix product, you will get, at least in terms of the row count, this matches. So the number of rows in My1 and the number of rows in My2, their product is the number of rows in My. And column count also matches. So we can potentially ask the question whether these two things are equal. Okay, so is there anyone who doesn't know the definition of tensor product?
We just put this matrix inside.
Yeah, I think this sometime we did say that sometime.
This is also in the previous course.
Right matrix. You put
Oh,
every entry.
that long ago.
You looked at this one.
So in general, tensor product of matrices is defined as so this really doesn't need any assumptions on the dimensions of the matrices. So for take any matrix A and any matrix B, they may not even be square matrices. And basically inside the matrix A, you have these entries Aij's. You just replace Aij by a matrix which is B scaled up. So you put B and you multiply every entry there by Aij. Okay, so this further expands as Aij dot BKL, and then do this for all IJKL. Okay, but the way you will organize the matrix is given in the middle, which is it's the A matrix with every entry replaced by a bigger matrix given by B. So right, so how, let us write the
You can also break.
dimensions. So you have M cross N, M prime cross N prime. Then the final number of rows is MM prime cross NN prime. Yeah, this is a weird construction. You may be ready to accept addition of matrices and multiplication of matrices, but may reject this definition of tensor product. So the simplest way to motivate this is when you look at a polynomial ring with one variable and go to two variables, what happens? Okay, so if you think about this for a day, then you will come up with this definition. So it's basically at the level of algebra, you are just increasing the number of variables. Okay, so that construction is it's a very fundamental construction, and it is called tensor product. Here explicitly it looks like this at the level of matrices. So what we have is, this question is then well defined. You take these two matrices, take the tensor product and compare it with the matrix for F1 times F2. So now how do you show that these two are equal?
Because the return is equal to something.
So you are looking at a coefficient of F1 and a coefficient of F2, and in the tensor product they will be multiplied. But since they come from, everything is disjoint, this coefficient also appears then in MYZ F1 F2. And moreover, when you multiply F1 with F2, the polynomial multiplication doesn't involve convolution. You are just picking one coefficient of F1, one from F2, and the product is a final coefficient. There is no convolution happening. So use all these assumptions. Yeah. So this follows from disjointness of the subsets. Which allows coefficient of my, mz, f1, f2 factorizes, simply factorizes to
Yeah, I mean, you want these small y1, small y2 disjunctive and these small y1 over all those kind of things.
sorry.
You also want small y1, small u2, this,
There is no small.
yeah, this y1, y2
Mhm.
disjonctive to be y, I mean,
But the
there are
all,
possible monomials that you're taking from those.
but all that we have.
Some of them you're taking, some of them you're not taking. So that is how you construct the monomials, right? M small y is basically small y is some subset of capital Y which you have taken and constructed the monomials.
No, so maybe I have jumped a step. Uh, so in any polynomial f, multilinear polynomial f, you can factorize it like this. This is correct, and f here will take f1 times f2. Yeah, so now when you look at the first extraction, this y1 z1 extraction from f1 f2, yeah, this will just extract the product monomial from f1, the coefficient from f1, because there can be no contribution from f2. So f2 can only contribute a constant term. So constant term of f1 times f2 is the only is a thing which is common in all these equations. So we have this property, and this property implies from the rank property of tensor matrices, so using the rank property of, so what is the rank of A cross A tensor B? Yeah, how do you show that?
Basis to basis and so on.
Yes, so that is a simple exercise. Using the definition, you can show that rank of A tensor B is equal to rank of A times rank of B. Okay, so in the end, it is a simple construction. The rank just multiplies. Yeah, so prove these things as an exercise. Then
The eigenvalues, the proof is easiest,
The
right?
eigenvalues should
The eigenvalues should be the
product
product.
of eigenvalues.
So you'll have some non-zero ones, and then the rank will be equal to the number of non-zero eigenvalues.
but what if you?
We have
But
mod square, yeah.
what if you don't know what eigenvalues are? So rank is visible, right? Eigenvalues is something very hidden.
You also need like the SVD or something because it's not even square.
Yeah. So no, easiest is just use rank by first principles. Yeah, I mean using the definition of rank, you can say that after a point the columns are just zero or something.
Maybe we could simplify it, like break B into.
Right, so then you go up to R1 columns in A and let's say R2 rows in B. Everything else you set to 0. And then you show that now for this chunk, the rank will be R1 times R2. Yeah, so I think by first principles it is the easiest and you don't need any assumptions. Okay, so using this coefficient extraction of f1 times f2, you get the tensor product, and from the tensor product now you get the measure, which will be gamma y z f is equal to the product of gamma yi zi fi. Okay, so we did this for product of two polynomials, but it's also true for any product. Same proof. So measure of f is equal to measure of product is equal to product of measures. Is that clear? Okay, so we can do one more property, or yeah, then we can leave. So they are all just basic properties of the measure, independent of the model. So this is multiplication by z free. So for any g non-zero, that is z free, which means it has only y variables. Okay, so remember that the measure is defined with respect to y cross, well, y in the row, z variables in the column. So if you have a polynomial that is z free, then the measure for it is just single column, right? So if you multiply by such a polynomial, then what happens? If you multiply f, which is an arbitrary polynomial, multilinear polynomial, if you multiply it by g and then look at the measure, yeah, it doesn't change. That's the claim. Exactly. So measure doesn't change if you multiply by z free g, or you multiply by a y free g symmetrically. Yeah, it's again simple, but we have to still be careful about this. So gamma of fg is equal to the rank of the derivatives of fg So I am saying that the measure is rank of the derivatives at z equal to 0, where the derivative is with respect to a monomial only in z. So it's a new claim. This actually follows M is the column in your matrix. So what does a column in your matrix represent? That is the question. It basically represents that you have differentiated f with respect to M, and then gotten a polynomial which is z free, so it is only in y, and its coefficients are put in the column, right? So think in those terms. So this represents a column. In the matrix. So the rank of the columns is exactly equal to the rank of the resulting derivatives, and at the point 0, z equal to 0. Y is not set to 0. So we are actually looking at polynomials in y. Z has been set to 0. So is this clear? So this also, just think about this. It follows from the definition of the matrix. So once we have this, what can you say about dou m f g? G doesn't have any z, so G comes out.
I was saying can't we prove this directly by applying previous formula? So G will be in only first column, and that is rank 1. So
But disjointness,
Rank of f times so G has variables in y, right?
So we just want gamma y comma z of
G has variables only in y, which are only in y, not in z.
so to break it fall down.
Or you
so,
are-
so this lemma,
Disjointness with f in terms of the y part where it does not have disjointness.
it is not disjoint.
yeah, it doesn't, it is not subsumed in the previous case. In the previous case, everywhere we used disjointness. This is something else. In particular, yeah, as they are saying, f and g have. So I am not assuming that f times g is a multilinear product. This is actually maybe I should write it down. Overlap in y. So G has y variables, F also has y variables. So both of them may have y1, and that may be giving you y1 square.
You are not partitioning y, but you are only partitioning z, and it also works.
Yeah, either way, you have to prove something else.
This is giving the proof.
You have to prove something else, which is this.
Which is this?
So
Combine this, we can say that.
so G is a non-zero polynomial. We have taken it out. So then we can just drop it. Which is nothing but gamma f. Yeah, G you can just drop basically. Yeah, and one last thing is, any questions about this? So last property will be upper bound on the rank, trivial upper bound. So for any so this is where we are assuming multilinearity actually first time. For any multilinear f, gamma yz f is upper bounded by what is the maximum for this?
Cancel columns. Like this
Right.
cancel column.
So 2 raised to min of yz. Is that clear? So just either minimum number of either number of columns or number of rows, whatever is smaller is an upper bound. So this just follows from the size of M, Y, Z, F matrix. But since this is so lazily done, do you think it is optimal? What is the example? Okay, thanks to Ram Prasad. So fx, you take
At least you start rotation.
sorry.
He said product of xi and yi. You could have at least used R notation.
So why is it everything?
That's not a good idea. I want to use my notation. So f of x is you take these x to be 2n variables, and these 2n variables, so first n variables are these yi variables, second the later n variables are zi variables, and look at this product, right? So what is the measure for f? So now use the lemmas. So this tensor product thing tells you that it is, yeah, so it will boil down to basically gamma of yi plus zi, and the measure of this is clearly 2, so you get 2 raised to n, which is the upper bound. it matches. Okay.